Hello, everyone, and thank you for attending this online presentation. I am Bernard Fon from the University of Southampton in a collaboration program with the Agency for Science, Technology and Research of Singapore. And together with my supervisors, Gabriel Weymouth, Bintan Nguyen, and Tutty, I'll be presenting our work titled Turbulent Wake Prediction using Deep Convolutional Neural Networks. So the research problem that we are interested in is how can we simulate flow path long and flexible structures in a computationally feasible time. So structures such as marine risers, tall pillars, or aircraft wings, they are long, they present a homogeneous direction, they are flexible, and doing a fully resolved three-dimensional simulation is nowadays very infeasible because it's very expensive. So this happens because they have like large aspect ratios, above 1,000. They operate in high Reynolds regimes, meaning there's a vast range of flow structures, and there's also the added complexity of fluid and structure interacting. So instead of doing these fully resolved three-dimensional simulations, some authors have been applying strip theory methods, which is basically a way to reduce the dimensionality of the problem from the original 3D domain down to multiple 2D planes. Here's a sketch of how this would look like. And with this, the computational cost of this simulation is greatly simplified. And one would solve the 2D Navier-Stokes equation in these multiple planes, the resolution of which depends on the structural modes of the cylinder. But there is a main shortcoming of these methods, and it's basically that the flow dynamics of 2D and 3D systems, these are very different. In particularly, in 2D, we have an inverse energy cascade where like vertical structures, they merge together and they become bigger and intense. And in the 3D, we have the classical direct cascade of large scale structures breaking down into smaller structures because of the vortex stretching method. So just from a qualitative point of view, we can see here how this would look like. This is a simulation of flow past a circular cylinder at Reynolds 10,000. On top, we have a two-dimensional simulation, and on the bottom, we have a 3D one with a span of pi diameters. And basically, it can be observed how the top simulation presents very coherent and energized vertical structures. Also, the roll-up of the shear layer happens quite close to the body. And on the other hand, the 3D simulation on the bottom presents like mid-scale structure or small-scale structures. They behave quite chaotically. The shear layer roll-up also happens a bit further downstream. And this means that when we are gonna measure like the forces induced to the body in the 2D case, it would be like over-predicted in comparison to the 3D counterpart. So this over-prediction of the induced forces is something that we want to avoid if we are going to have a dimensionality reduction problem. So to add these 3D effects that kind of add some dissipation mechanism to our 2D Navier-Stokes equations, we have considered local spanwise averages of the flow. And we call this method the spanwise average Navier-Stokes equations. And differently from the standard strip theory method, every strip that we have here, this represents the local flow average. So it consists of the spanwise average part and the spanwise fluctuating part. This spanwise fluctuating part is what adds the 3D effects into the 2D solvers that we are looking for, and that would eventually bring us back the spanwise average solution of the flow, as you can see in this simple equation here. So from a mathematical point of view, the spanwise average Navier-Stokes equations are just a flow decomposition based on the local spanwise average of the flow. And this is in addition to your ILES solver, or LES solver, or RAND solver, whatever you have in your original 3D domain. Then on top of that, you do this dimensionality reduction technique using this spanwise average operator. So what you end up with is your 2D Navier-Stokes equations, which already include the turbulence model of the subgrid scales or or the time fluctuating part as you wish. And then we have a closure term for the span-wise fluctuating part, which represents this information missed during the average. So our base flow here is just a 2D flow, but when we add our closure terms, we recover the span-wise average solution of the flow. The terms look like it would normally do in a Reynolds decomposition. So we have like a stress tensor. Here we call it the span-wise stress residual tensor in red. And the divergence of this tensor is what it shows up in the momentum equations. But just because one might want to avoid taking derivative of potential closures that are applied to this span-wise stress residual tensor, it could also be taken into account from what we call the perfect residual closure, in which the spatial discretization of the equations is already included. So you don't need to, in your potential closure model, you don't need to afterwards take a derivative of your outputs, which would amplify potential noisy prediction. So in this work, we will focus on the closure of this in blue that we see here. That is a direct source term for the momentum equation. Again, adding this source term to the momentum equation changes the flow dynamics from a classical 2D to this span-wise average picture that we were aiming for. So from a qualitative point of view, here if we start from a span-wise average snapshot in a 3D simulation, and we let this evolve like 2 convective time units. On the bottom left, we have what we would obtain if we don't include these span-wise fluctuating terms. So you see how the wave has already rapidly 2-dimensionalized, and we see again the large-scale, coherent, energized vertical structures that in the end makes you over-predict the forces induced to the cylinder. But on the other hand, when we include these closure terms, we get this span-wise average, we recover the span-wise average flow, and we would observe or measure on the body the correct induced forces such as lift and drag. So now we have a way to go from 3D to 2D, in which we account for 3D information that gives us back a physical answer on the forces induced to the cylinder. But we have some closure terms that we need to model. These closure terms, one might try to tackle it using some of the currently available closures for turbulence. But then again, what we are trying to solve here are not subgrid scales or are not a dissipative term. What we are trying to solve here is a 3D-like term that when you include it to your 2D equations recovers the span-wise average solution. So eddy viscosity models in principle shouldn't be well suited. But well, we had a closer look at this. And here we try to take into account the Busensk hypothesis, where the anisotropic part of our closure tensor is related to some turbulent viscosity times the span-wise average the span-wise average rate of strain tensor. So if we have a look at how these resolved and closure quantities relate to each other through density plots, as you see here, you can observe how the normal components of this anisotropic stress tensor and the shear components, they are very differently related to our resolved quantities. And obviously, if we are going to map these quantities using a scalar field, it wouldn't be impossible because we need to map closure terms and components to the resolved quantities. So a scalar field, whatever we use to model this turbulent viscosity, it can use like a Smagorinsky model or whatever, it wouldn't probably work. So what we did then is to turn our attention into data-driven methods. So in a 3D simulation, we can just generate a data set of span-wise average quantities, resolved and closure ones, here like in capital U and SR respectively. And we can feed this data set into a data-driven function that provides this mapping that we need to. So in this sense, we selected convolutional neural networks because they have some intrinsic properties such as translation invariance, which are very advantageous for our model. So basically, whatever feature of this of this mapping resolved quantities to spanwise fluctuations, it finds this can be applied to any point in the domain because of the translation invariance. And also they have proved to be quite good at revealing like some hidden correlations when we have a physical term that there's no information a priori. Like we don't really know how these spanwise fluctuating terms behave. On the other hand, as I've mentioned before, here we will be targeting the divergence of the spanwise stresses residual tensor instead of the tensor components, because we don't want to apply a differential of, like, we don't want to differentiate a potentially noisy output of our machine learning model. So to build these convolutional neural networks, mapping resolved quantities to spanwise fluctuating closure terms, we tested different architecture, loss functions, activation functions, and we also assessed different networks, like networks having different number of trainable parameters through maximum number of filters and kernel sizes. And then again, we also tested different inputs, such as the ones that you see here, input sets, to see whether providing potentially closer answer as input to the spanwise fluctuating terms would be beneficial to the neural network. So to test every of these parameters, we fix the other ones in what we call the base case parameters here in blue, and just assess the performance of these different metrics. So we start with model architecture and data normalization. So all of our convolutional neural networks are based in autoencoders, which basically they take whatever input, they map it to a smaller latent space, kind of trying to find maybe global coordinates of this function, which then they can revert or map to the closure terms in this upscaling or decoding branch. So our neural networks, they have multiple inputs because we have different data set input sets that we are trying, and then these have two outputs, which are the x and y source terms of the momentum equations. So we tested 3 different models, some of them including like a full autoencoder branch for each input. The second one also adds an additional autoencoder branch before the output. And then we have the third one where the latent spaces of each input branch is concatenated and then it's separated again to our outputs. So first of all these models provided quite good correlation coefficient in terms of Pearson correlation coefficient between target and predicted fields, which means that this is already quite a good architecture to start with. And then we also could observe how the architectures with a higher number of trainable parameters were performing better by providing higher correlation coefficients compared to the other one. And then we also tested how the normalizing the input data affects these predictions. So using each individual snapshot standard score before normalizing it with the standard score before feeding it to the neural network normally provides a faster convergence during training. So that's something positive as well. Then we tested the different activation functions and loss functions. So for the activation functions, they typically used in neural networks nowadays are the rectify linear unit function, but with other functions that were tested before were the sigmoid or the hyperbolic tangent functions. And we could observe how the ReLU function was better because it preserved the intensity of each neuron across the layers. So this is not capped at some maximum value. And this has been positive for our test case as well as many other neural networks lately have been showing that this function works very well. We also observed this, that the ReLU function provided higher correlation coefficients. And then we tested different loss functions. So our target data, these perfect closure spanwise fluctuating terms, how can we fit it using like a sum of the squared error or the sum of the absolute error? And what we observed is that the sum of the squared error was performing much better than the absolute error. And this is probably linked to the fact that the absolute error presents a singularity at 0. And this is like not smooth, whether whereas the sum of the square error is overall a smooth function, so it's easier to differentiate them and maybe can achieve better local minimas compared to the absolute error function. So then we also tested the number of filters and the kernel size of this convolutional neural network. And basically the number of filters, what we did was to fix the number of filters at the latent space. So using like 16 or 32 or 64. And our encoding branch was increasing up to 64 and then decreasing or to 32 or 16. And this is how we have modified the number of trainable parameters as well. And we could see that similarly to the architecture hyperparametric study, the one providing like having a higher number of trainable parameters, here would be the 64 filters in the latent space, was showing better performance in terms of higher correlation coefficient. And finally, we also tested different kernel sizes for these filters. So it's a 3x3, 5x5, or 7x7. 3x3 would be the minimum kernel size you would need to detect the flow structure in this case. And then 7x7 would be here like an arbitrary choice where we would already be kind of missing the small scale structures a bit. But well, we could observe how like a compromise within these two, the 5x5 was providing like better predictions. And probably this is due to the fact that it's focused on the small scale structures more than the 7x7, but it also has some detection of large scale structures. And then whatever larger scales they don't fit into is 5x5. This can be obtained through the nonlinear combination of the filters. So it can learn how to overall map large scale structures that doesn't fit within the kernel size. So, and last, we tested what input set was working better to map these resolved span-wise average quantities to our span-wise fluctuating closure terms. So we tested primitive quantities like velocity, pressure. We also tested span-wise vorticity and a distance function. And finally, we tested like a gradient set. So we have like the Jacobian matrix of the velocity flow field and the gradient of the pressure. And we see that the primitive input set and the gradient input set was the ones providing the highest accuracy, like 86% correlation. And then we have the other one with the vorticity and the distance function was just about 50% correlation. So it could be argued that maybe including the pressure is important in this case, but this has not been tested in direct comparison. But it's also important, as we can see, like to include the different gradients because it also provided a good correlation coefficient. However, because the primitive input set was not providing any gradient and still had a high correlation coefficient, one could maybe conclude that the neural network is learning these spatial gradients on its own, just providing the primitive quantities. So that was something positive as well. And finally, we went to our best model prediction. This would be like combining all of the best answers that we got during this hyperparametric analysis. So this would be using our larger architecture, the third model, where the concatenation happens in the latent space. Then we had the sum of the squared error, a maximum number of filters of 64, and then a kernel size of 5x5. And finally, we use here the primitive input set, just because it was providing the same kind of left correlation as the gradient input set at a lower cost, because we had less input branches. So with this, we were obtaining like 89% correlation between target and predicted fields, which we were very happy about. And here, from a qualitative point of view, we have on the top left, how would this look like, this closure term that adds the 3D effects into the 2D Navier-Stokes solver that I was probably mentioning. And then what is the raw prediction of our machine learning model on the top right, and how can this be post-processed? So basically, we can see that, again, mid-scale, large-scale structures are currently captured here. But there's some noise that you can observe in the near region to the body. There's also like not a very good correlation on the small-scale structures. And this is definitely something that has an impact on a potential a posteriori framework And this is some done that we have, some work, sorry, we have done already, and we've published a preprint that you can check out if you're interested, where we have this a posteriori analysis, and also we try to assess the generalization of this model to other flow configurations. But to the point where I wanted to go is that when we add a noisy prediction in this autoregressive a posteriori setup, this contaminates the resolved quantities in a divergent manner that makes your simulation go completely unphysical. So a way to mitigate this, not fully resolved, but to mitigate, is to post-process your machine learning outputs and applying some Gaussian filtering, getting rid of these high frequencies, and maybe also like a wake mask where the trivial regions of this wake, like where there is like an altered flow, this wouldn't be predicted by the machine learning. So we try to stay focused within the non-trivial region, and we filter out the high frequencies. So this is how this post-process machine learning prediction would look like in the bottom right. Just to conclude, so like the general ideas that I have introduced are the fact that we are able to run a 2D solver with some additional closure terms that incorporate like three-dimensional effects, and this reduces the dimensionality of a problem from 3D to 2D. So there's there would be like a potential important speed up of the computational time of the original problem. And these closure terms, which incorporate the 3D information, we've checked that A viscosity models are a priori not very well suited for this. So instead, a convolutional neural network can successfully learn to map our resolved spanwise average quantities to this closure spanwise fluctuating terms. And we have checked the architecture of this model, the different activation functions, loss functions, and so on. And we have ended up with the best model possible, yielding around 89% correlation. And finally, I'll mention the fact that there is a lot of challenges in implementing this in a posteriori setup, but this is something we've worked more in detail in our latest preprint. So again, check it out if you feel like. And yeah, that's all. So thank you very much for attending this presentation. I hope you have enjoyed. And if you want to download the slides, you can scan this QR code or send me an email. So thanks again, and I'm looking forward to your comments. Thank you.